Thank you so much. I feel incredibly honored to receive the Major Distinguished Faculty Lecturer Award. I'm so grateful for the opportunity to work at Brigham Young University. I've always loved BYU. When I was young, I loved watching BYU football, and I loved attending BYU as a student. I consider my employment at BYU and my interactions with the many wonderful students and colleagues to be one of the great blessings of my life. My background and training is in the area of robotics. As a graduate student, I studied robot manipulators and their applications to space and manufacturing. I had the good fortune to come to BYU at roughly the same time as Professor Tim McLean in mechanical engineering. We were both young faculty with similar backgrounds, and we were both trying to figure out how the academic world worked. We immediately struck up a collaboration and a friendship that has now lasted for 22 years. Most of the work that I talk about today was performed in close collaboration with Tim, and I want to gratefully acknowledge his contributions and the significant influence and impact that he has had on my career. In our world today, autonomous vehicles are everywhere. One of the most common examples of is an autonomous vacuum cleaner. Even though they can be frustrating when they don't work, an autonomous vacuum is an amazing piece of technology. It explores your home, detects dirt and obstacles, and recharges itself when it's low on batteries. Another well-known example of an autonomous vehicle is the Mars rover program. The first rover went to Mars in 1997 and remained operational for 3 months. The next rover lasted for almost 7 years and covered almost 5 miles. There are currently 2 operational rovers on Mars that have been there for many years and that primarily operate autonomously and are capable of analyzing the environment using a variety of sensors and then broadcasting those readings to Earth. Another example of an autonomous vehicle is a self-driving Uber. Prior to the recent accident in Tempe, Arizona, you could order a self-driving Uber where the car is acting completely autonomously with the driver sitting in the front seat for safety reasons but not operating the car in any way. In the video you see a LiDAR system on top of the car. You can see the system is actually reconstructing the environment, will stop for obstacles, and is driving the vehicle autonomously. As you know, the military has been operating drones for some time. The Predator drone is an unmanned but remotely piloted vehicle that's remotely piloted by operators who may be halfway around the world. At the other end of the spectrum, you can go to Walmart and purchase a drone with a camera for less than $100, or you can buy one off the internet for less than $50. There's actually some pretty sophisticated technology that's on these drones that they use sensors to stabilize the platform so that operators with very little experience can fly the vehicle. For more money, you can purchase a commercial drone with very sophisticated autonomy features. The drone that's shown here in the video enables the operator to think of this drone as a flying camera. It will actually avoid obstacles in the environment, automatically follow a specified target, and return to a launch point if you get lost. You can even fly it with as if it were a virtual reality machine, which is pretty amazing. Given the wide range of autonomy functions, the self-driving car industry has defined 5 different levels of autonomy, starting with no autonomy at level 0 and moving to full autonomy at level 5. For example, a radio-controlled aircraft where the pilot maneuvers levers on his transmitter to directly move flaps on the aircraft is an example of no autonomy or level 0. The Predator drone, or the Tiny Whoop drone, where the computer stabilizes the platform, but the pilot directs and otherwise flies the aircraft, is an example of level 1 autonomy. The DJI Mavic that I showed in the previous video, where the pilot gives high-level commands like follow me or fly home, and where the computer then flies the aircraft, is an example of level 2 autonomy. A self-driving Uber, where the driver remains in the car but only takes over when necessary, is an example of level 3 autonomy. The Mars rover, where the operator gives very high-level commands, but where the robot otherwise operates autonomously, is an example of level 4 autonomy. Finally, the robotic vacuum, which in principle can operate without human intervention, is an example of level 5 autonomy. These definitions define the goals and the objectives of the self-driving car and self-flying car industries. There's no question that we are in the middle of a revolution in autonomous vehicles and autonomous machines and intelligent machines in general. But why is this happening right now? In the mid-1990s, when I started working at BYU, there were 4 technologies that had recently been introduced to the commercial market that would have significant influence on robotics and that would enable the current boom in autonomous and intelligent systems. The first of these technologies is the Global Positioning System, or GPS. The GPS system was developed during the 1970s, primarily for the military. The first commercially available GPS receiver appeared on the market in 1989. The full constellation of 27 GPS satellites became fully operational in 1993, and selective availability, which artificially degraded the quality of GPS, was discontinued in 2000. GPS is an essential technology for autonomous systems since it allows vehicles to know where they are on the Earth and to plan and execute maneuvers relative to their location. The second enabling technology was the development of MEMS, gyros, and accelerometers. A gyroscope is a sensor that measures angular velocity, and an accelerometer is a sensor that measures acceleration. Gyroscopes and accelerometers are necessary to enable stable autonomous flight of traditional fixed-wing aircraft, helicopters, missiles, and satellites. Gyroscopes and accelerometers were developed and have been widely used in the aerospace systems since before World War II. However, traditional gyroscopes and accelerometers are designed using mechanical parts that, while highly accurate, are heavy and very expensive. For example, high-end accelerometers and gyroscopes cost tens of thousands of dollars, and high-end accelerometers and gyroscopes used on intercontinental ballistic missiles can cost hundreds of thousands of dollars and may weigh many pounds. MEMS stands for Micro Electrical Mechanical Systems and is the technology that allows small moving parts to be embedded in electronic chips. The first MEMS accelerometers were developed in the automotive industry in the early 1990s for use in airbag systems. Today, MEMS gyros and accelerometers can be purchased for less than $10 and are found all around us in smartphones, Wii consoles, Fitbits, and many other commercial devices. MEMS gyros are absolutely essential for small quadrotor style drones and for flying robots in general, since they are used to stabilize the platform so that a human operator can easily control them through simple high-level commands. A third essential technology enabling the current boom of unmanned systems is low-cost, low-power, small embedded computers. Computers provide the brains for perception, planning, and control. The first microcontroller was produced by Texas Instruments and appeared on the market in the 1970s. However, it wasn't until the 1990s, with the invention of flash memory, that they became practical for use on mobile robots. Today, there are small, inexpensive, low-power, embedded computers that can run very sophisticated computer vision algorithms and machine learning algorithms. The state of the art in this area is really quite amazing. The final essential technology for unmanned systems is high-energy density batteries. The lithium polymer battery found in your cell phone were first commercially available in the early 1990s, but they were not practical for use on RC-size aircraft until the late 1990s. Therefore, in the early 2000s, when we were getting started, there was this perfect storm of available technologies that enabled unmanned aircraft and mobile robotics in general. However, the real enabler has been that each of these technologies are perfectly aligned with their use in consumer electronics. Each of you here today are probably wearing or have in your pocket a device with accelerometers and batteries and an amazing computer. And so the economy of scale has driven development and has made these technologies extremely inexpensive. So how do self-flying and self-driving vehicles work? So this figure shows a high-level diagram of the components that are required for a self-flying vehicle. Of course, the most essential element is the physical aircraft itself. One of the distinguished characteristics of any autonomous robot are the sensors. Self-driving and self-flying vehicles have two types of sensors. First, internal-looking sensors like gyroscopes and accelerometers, or an odometer in a car, and we'll put GPS in that category as well. And also external-looking sensors like a camera or a LiDAR or a radar. So the internal-looking sensors monitor the state of the robot itself, whereas external-looking sensors are used to monitor the environment, to detect things like pedestrians or buildings or things that might cause a collision. For example, on a self-driving car, the internal sensors include the wheel encoder and GPS. The external sensors include radar, LiDAR, camera, and ultrasonic sensors. In the block diagram, the internal sensors, or flight sensor in this case, are the input to an estimation algorithm that estimates the position, angular velocity, and velocity of the aircraft. This information is then used in a flight control algorithm to fly the vehicle. The external sensors and the state of the aircraft are the input to a perception algorithm that estimates objects in the environment, like buildings or pedestrians or other cars. A prediction algorithm then predicts what the environment will look like in the near future, for example, over the next several seconds. A planning algorithm then decides how and where the robot should maneuver based on the predicted future. For the remainder of this talk, I'm going to provide examples of each of these blocks by discussing some of the work that our lab has been doing in the area of self-flying vehicles. This is a recent picture of students in our lab with some of the aircraft that we work with. Our specialty has been small fixed-wing aircraft, but we are currently doing extensive work with multi-rotor systems as well. Our research over the years has been focused in 4 areas. We've worked on cooperative control, where the objective is to develop algorithms that enable robotic vehicles to cooperate to perform tasks. We're currently working in the area of computer vision-based control, where onboard cameras and other sensors are used to reconstruct the scene and then maneuver a flying robot. We've also developed an autopilot system for small fixed-wing aircraft that resulted in a spin-off company and is currently commercially available. This video illustrates some of our early work on the Kestrel Autopilot system. In the video, you see an aircraft that is flying through Goshen Canyon in Utah using optic flow sensors. We've also done a lot of work on multi-aircraft systems, including formation flying, as you see here in the video. This next clip shows one of our only recorded mid-air collisions with a successful recovery. It's hard to crash these things. This next video shows a project we were working on where you had simultaneous arrival of multiple aircraft at the same point. This is difficult because of wind and other environmental conditions. And of course, autonomous landing. I'll now talk about some of the work that we've been doing on perception. Perception is the process of interpreting the output of sensors on board the aircraft. One of the primary sensors is a digital video camera that returns 3 arrays of numbers, one for red, one for green, one for blue, at approximately 30 frames per second, which for a 1080p camera amounts to 6.2 megabits per second. The objective is to interpret all of this data and then take action on the data. The reason why this is hard is illustrated in the slide in the display. While we see with our eyes a nice image of campus, the computer sees 3 massive arrays of numbers between 0 and 255. From these numbers, the computer must detect lines, color patches, buildings, people, anything else we want it to see. This next video shows some recent results of our lab using computer vision techniques to track many moving objects from a moving camera. This is a difficult problem because both the camera is moving and also the people in the image are moving. One of those people may be you. This is on BYU campus. So how does this technology work? If the camera is not moving, then we can detect moving targets by subtracting the current video frame from the previous video frame. Pixels that are different then indicate potential moving objects. If the objects persist over multiple frames, then we can fit a motion model to that data. An example of a motion model is a trajectory that moves along straight lines at a constant velocity. The challenge with this project is that the camera is on board an aircraft that is also moving. To deal with that challenge, we first estimate the video motion due to the aircraft and then look for residual motion on top of that. Potential applications of this technology include search and rescue, and also wildlife monitoring. This next video shows another project where the objective is to enable a multi-rotor aircraft to navigate indoors with vision only. The insert on the right shows the robot's camera view, and the insert on the left shows the reconstructed scene of the environment. The yellow disc are obstacles that have been identified and are to be avoided. You can see in the upper left, the point cloud model, you can clearly see the desk there in the environment that's being reconstructed in 3D from the video feed. So how does this technology work? The basic idea is to identify similar features in two sequential video frames. For example, strong corners in the image make good features and are easy to identify by looking at color gradients. If the robot moves between frames, then there will be a parallax between the two images, and that parallax can be used to triangulate the 3D position of the features. This is similar to the way our eyes reconstruct a 3D scene. The 3D position of the features can then be used to create a voxel grid map of the environment, as shown in the lower right corner, and then that environment can be used for subsequent path planning. Potential applications of this technology include following, for example, a mountain biker through a complex environment. In the video, a 3D voxel grid of the world is being used to maneuver the aircraft around trees. Another project that we've been working on is GPS-degraded navigation. In this video, a multi-rotor is navigating through the Fletcher building on campus using several complementary sensors that include an RGB camera, an infrared depth sensor, and a GPS unit that receives occasional measurements when it is outdoors. The multi-rotor is first guided by a human to close a path in the environment. When it gets back to a position that it recognizes that it's been before, you'll see in the lower right small yellow lines that indicate that it has seen that position before. When it recognizes a position that it's been before, it then optimizes the map, and at that point can navigate autonomously relative to that map. At some point, when it's outdoors, it'll receive a GPS measurement, as you'll see here in a moment. As soon as that GPS measurement is received, then the robot can localize itself in the world. It knows it's on BYU campus, for example. So how does this work? So the robot begins in an unknown location, at least unknown to itself, and takes an image of the world, or a keyframe of the world. It then moves and compares subsequent image frames with the original image to estimate its motion relative to the key frame. It continues this process until most of the original features in the original image go outside of the field of view. The robot then establishes a new keyframe, and the process continues until the robot recognizes that it has returned to a previous location, which we call a loop closure. The motion around the loop is then optimized to resolve discrepancies caused by noise in the sensors to produce a consistent estimate of its motion. There are many potential applications of this technology, but some include bridge and other infrastructure monitoring where GPS signals are intermittent or non-existent. I'll now talk briefly about prediction and planning. This video illustrates a project we had several years ago where the objective was to use onboard computer vision to land an aircraft in the back of Dr. McLean's truck. The computer vision algorithm is looking for the biggest red object. Of course, sometimes things don't always work out so well, and when it's looking for the big red object, it hits the tailgate. We were just glad it didn't hit the stop sign in the background. So how does this technology work? So the basic insight comes from ship navigation and missile guidance. The aircraft will be on a collision course with the truck if the truck remains stationary in the image plane of a forward-looking camera. Ship navigators use this idea to navigate relative to lighthouses. Therefore, the aircraft is maneuvered in a way so that the truck, or the largest red object, remains stationary in the image plane. Again, there are many applications of this technology, but some include Drone package delivery, we're all waiting for that on campus, right? And military convoy support. Another area of research in our lab is path planning and collision avoidance. This video shows a simulation of a fixed-wing aircraft flying through a cluttered urban environment using computer vision to avoid obstacles. So how does this work? Consecutive video frames are processed to create a depth map, as shown in the lower left of the video. The depth map is then processed to segment distinct objects in the environment, creating a low-resolution, robot-centric 3D map of the world, as shown in the upper right. And then a path planning algorithm is used to create a trajectory through the world that will avoid obstacles, as shown in the lower right. So I've mentioned path planning a few times. How does path planning work? Path planning has been an active area of research in the robotics community for the past 40 years. There are many approaches to this problem. I'm going to describe one simple algorithm that's easy enough for me to explain to you, and that is computationally simple and has been successfully used in many different robotic applications. The technique is called the rapidly exploring random tree algorithm. The algorithm is initialized with a start and a goal location, in addition to the location of a number of obstacles. The algorithm then randomly picks a point P in the environment and extends a path from the start location in the direction of P. Another random point is then generated, and the search tree is extended towards P from the closest point on the existing tree. If, in this process, a collision is detected, then the point is simply discarded and a new point is randomly selected. The process continues until the tree can be connected to the goal location. The RRT path planning algorithm, although very simple, has been successfully utilized in a variety of different applications, including unmanned aircraft, self-flying cars, driving on slick roads, robot manufacturing, and even solving those little games that you get for Christmas that drive you crazy. Where is all of this technology going? So currently there are major advances happening in two related areas: autonomous aircraft systems and self-driving car technology. In the future, these technology thrusts will converge and will result in the next revolution of self-flying cars. In case you think this sounds like science fiction, I want to show two promotional videos from Kitty Hawk, a small company in the Bay Area that employs former members of our lab. This video shows a prototype of a self-flying taxi that is scheduled to begin operation in Australia in 2021. So in the video, this aircraft is flying completely autonomously. The concept is that the self-flying taxi will operate much like a bus service. You will go to a terminal pad, get in the self-flying taxi, use your smartphone to select the next terminal pad that you'd like to go to, and then the self-flying taxi will take you there. The aircraft in this video is an electric vehicle with a limited range of about 60 miles. And you'll notice that the propellers on the wings that are upward looking are very short and stubby. That's to reduce the noise pollution caused by this aircraft. This next video is of a recreational flyer that operates much like a commercial drone. This is also a Kitty Hawk vehicle. But instead of an operator using a radio-controlled transmitter, it's sitting on the aircraft. This flyer is also electric, has about 30 minutes of flight time. The idea is that these flyers will be offered first for recreational use until a sufficient safety record is established, and will then be transitioned to a personal flying machine that could be used for commuting and other activities. I want to note, too, that this isn't a hovercraft. This is actually a flying vehicle. It's not limited in altitude. It's not limited to water. But the idea is that you would fly it over water until sufficient safety considerations have been addressed. Doesn't that look fun? There are many other companies developing self-flying cars, many of which have working prototype systems today, and it seems like are constantly in the news. So before self-driving cars become a reality, there are many issues that need to be resolved. For example, legal issues. Who is responsible when there is a serious accident? Is it the passenger or the owner of the vehicle? Is it the manufacturer or the software engineer? There are also ethical issues that need to be addressed. For example, if the brakes go out in a self-driving car and there's a choice to either run into a barrier that will likely kill the driver or turn into pedestrian traffic, potentially killing many pedestrians, how should that choice be made? At the moment, we trust human drivers to make split-second decisions in those cases. And if you think about it, that is a very scary thought. However, with self-driving cars, we write algorithms that make those decisions. And the algorithms are developed well before the scenarios are encountered. So what is the right answer? Would you buy a car that you knew was programmed to save the most lives possible, even if it was at the expense of you, the driver? Another issue that needs to be addressed is air traffic management. Self-flying cars add a whole new dimension to safely managing the airspace that is not well suited to our current model of air traffic controllers, sitting in towers at airports. Should self-driving cars be allowed to fly anywhere, or do we maintain the notion of roadways or flight corridors? There are also serious technical challenges that need to be addressed, including autonomous sense and avoid algorithms that maintain the safety of our airspace. Having said all of that, and recognizing that prediction is hard, especially about the future, this slide shows my guess at a possible timeline for self-driving and self-flying cars. If I'm right, 5 years from now, those with a lot of money will be able to purchase a self-flying recreational vehicle. There will also be limited self-flying taxis in large cities, but likely outside of the US because of regulatory issues. In addition, we will see limited drone delivery from companies like Amazon. 10 years from now, level 4 autonomy. Right now, the Tesla Autopilot is really a level 3 autonomy system. So level 4 autonomy will likely be a standard option on many cars. Drone delivery will be commonplace. Self-flying taxis will be introduced in major urban areas. And we will begin to see commercially available self-flying cars, but probably outside of the US, again for regulatory issues. 15 years from now, there will likely be a strong transition away from car ownership as self-driving taxis become ubiquitous. This is already happening in large cities where millennials take Uber and Lyft. Self-driving taxis will also become, or self-flying taxis will also become commonplace. 20 years from now, self-flying taxis and self-driving cars will likely be an accepted part of the transportation infrastructure, and self-flying cars will likely be available for purchase at prices that may be affordable for the masses. In summary, the drone revolution is upon us. I've explained this revolution, why this revolution is happening now, and some of the technologies that have enabled it. Since self-driving and self-flying vehicles will impact all of us, I've attempted to help you be a smarter consumer of this technology by explaining some of the algorithms that enable self-flying and self-driving vehicles in the context of our research here at BYU. I have offered some ideas about what the future might hold. I hope you agree that the future in this area is exciting. Now, in conclusion, I would like to shift gears a little bit and offer a few insights that I've learned in my time at BYU. My first comment is to say that I resonate with President Nelson's story about standing in the operating room, not knowing how to proceed with an operation, pleading with heaven for help, and seeing a diagram of the required procedure open up to his mind. I've obviously never been a doctor in an operating room, and my experiences have not been as dramatic, but there have been several times in my professional career when I've struggled with a technically challenging problem and have not known how to proceed. I too have pleaded with heaven for help with those technical problems, all of which were related to unmanned autonomous robots. And there have been moments, a few precious moments, when light has poured into my mind with an idea that has enabled our research group to make progress. Having said that, I do want to say that in most cases, the progress has come line upon line, precept upon precept. The Book of Mormon teaches that the Lord works by means to bring about his great and eternal purposes, and that by small and simple means are great things brought to pass. If that is true with spiritual things, it is certainly true with technical research. The progress is slow. However, if we work at it, paying the price to understand the technical issues at a deep level, the help of the Lord will come. I distinctly remember a time soon after I started my career at BYU when I was feeling discouraged and was wondering if I could be successful in academia. I remember pleading with the Lord for help and for guidance, explaining that I wanted to do impactful work that would be a blessing to students and that would bring honor to BYU and to the church. That prayer was not answered immediately, but I decided to follow President Hinckley's advice to get off my knees and go to work. As I look back over the past 22 years, I can see clearly the hand of the Lord in my career. And there is no doubt in my mind that that prayer offered many years ago has been answered, and to a degree that I could not have imagined at the time. You too, have great things to do. Our society is facing many daunting challenges, and the world needs hardworking individuals with technical expertise who are also in a position to receive the direction and the guidance that the Lord is able and is willing to give. You can be one of those individuals. Plead with heaven for help in school, that you might be prepared for your future career. When you are in those careers, plead with heaven for help, and then go to work and do your best. In that process, I'm confident that help will come. And as President Benson promised, the Lord will make more of your life than you could make of it by yourself. And I say that in the name of Jesus Christ, amen.